Hi, guys. We're going to give it a minute for others to join the class. How you guys doing this morning? Good. We're coming up on rapidly approaching the end of the semester. I published all the rest of the weeks for the semester. So you can see lecture examples and homework assignments and stuff that are rolling through for the rest of the semester. We've got this week, which is a full week of classes. Next week, we only have class on Monday because it's Thanksgiving week. So there's only class on Monday. The rest of the week, Northeastern has off. So the 23rd, give me a sec, the 23rd, next Monday, will be our class that week. And then the rest of the week, we don't have it. When we come back, right, from Thanksgiving, we'll have a full week, November 30th, December 2nd, and December 3rd. I'm looking at a calendar. And then the week after that, we just have Monday and Wednesday. Okay, so we're wrapping up all of this stuff that we're talking about, okay? So kind of get a feeling for, if you look on the modules page, you'll be able to see all the things that are coming down the pipeline for what's going to be happening. I'd like to spend the last 2 classes, right, which is, I guess that would be December, let's see, December 7th and 9th. Those are our last 2 classes. I like to spend those reviewing for the final exam. So as we get closer, like in the next, couple weeks or so after Thanksgiving, I'll start posting old final exams on our last week's module page. Okay, so you guys can see old final exams. And then we'll spend those 2 class periods. I'll answer whatever questions you have on old homeworks, on old quizzes, on final exams, whatever you guys want to ask me about. Then we can just basically review those stuff there. Anyway, so that's what's coming down the pipeline. So keep in mind, right, we're wrapping it up. I will continue to accept old homeworks. I know that we have a whole bunch of solutions online. You guys can feel free to look at those and fill in the blanks for your old homeworks and then submit for full credit back if you want. Let's see what else. Yeah, and then we have homeworks coming up due. Okay, as we get closer, maybe like within a week before the end of the semester, I'll start posting solutions for the homeworks since the midterm exam. So you guys can start, using those to study for the final exam as well. But I'll post those up online in the next couple weeks or so. So kind of keep that in mind. We're rolling down the window here for the end of the semester. It's very exciting. All right. So before we get started on our chapter section, I wanted to talk about the quiz. I posted solutions for our quiz up online already. It's on the modules page where the quiz was announced. Right underneath that are the solutions for the quiz. But I just want to talk about some of the mistakes that I saw. Let's see if I can get this to focus. Good. Some of the mistakes that I saw repeatedly, and a lot of different people did this, not a lot, but most of you guys got the general idea. But so question number 1, let's go over. So as x goes to infinity, we've got the natural log of 3x divided by x squared. So there are a couple things. Some of you guys got the general idea, but you rolled through, you did this, he just went right into taking the derivative, whatever, and giving me an answer. Okay, that's not going to fly. You need to first do the first step. Step 1 is to do your check. So you have to substitute in as x goes to infinity. What is my numerator? What is my denominator? You must show that this limit is in indeterminate form before you move on to L'Hopital's. If you just plow right through L'Hopital's and you don't even state what you're doing, you're not going to get full credit on the final exam. I've seen it before when these things get graded. You have to state all of your steps and you have to state all of your work, okay? So as x gets really big, our natural log function, it's an increasing function. So as x gets super big, this thing is going to infinity, right? As x gets x squared also gets really big. That thing is also going to infinity, right? So I've evaluated this limit. I've got infinity over infinity. This is an indeterminate form. I must show this at the very least. You don't have to write indeterminate, but you must show it's 0 over 0, it's infinity over infinity, it's infinity over 0. You have to show that it's in indeterminate form. If you don't, you're gonna get points taken off, which is what happened on the quiz. Okay, you guys got points taken off. Our next step is, because it's indeterminate, I can do L'Hopital's rule. Okay, the next thing is you have to state that you're doing L'Hopital's. You have to write it. Okay, you have to show it's indeterminate, and you have to say specifically that you're doing L'Hopital's. Like I said, if you just roll through limit, 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 and I have to kind of figure out, like, what are you doing here? It's not going to fly on the final exam. Okay, you're going to lose credit. So remember, L'Hopital's, I take the derivative of the top. So when I take the derivative of natural log, let's just do this off to the side, natural log of 3x, right? So when I go to take the derivative of natural log of 3x, it's like natural log of u times du. So that's 1 over 3x. Chain rule says I have to take the derivative of what's inside. So the 3's cancel. This is just equal to 1 over x. Okay, don't forget your chain rule. You can also think about this in terms of your properties of logs. So this is natural log of 3 plus natural log of x. Natural log of 3 is just a number. Natural log of x is 1 over x. Okay, so that's kind of, this is how I thought about it, but you can do it with the chain rule. Okay, so when I take the derivative of my numerator function, I get 1 over x. When I take the derivative of my denominator function, be very careful. You're not taking the derivative of 1 over x squared. No, it's just x squared. So that's 2x. Okay, so I've got 1 over x divided by 2x. Now be very careful. Some of you plugged in as x goes to infinity here. Okay, if you plug in as x goes to infinity, I'm going to get 1 over infinity divided by infinity, which is 0 divided by infinity, which technically is also indeterminate. Okay, so before I do this, I need to simplify. Okay, before I proceed, I want to simplify. So this is like 2x over 1 over 2x. I've got a fraction divided by a fraction, so this becomes the limit as x goes to infinity, 1 over 2 times x squared. Okay, so clean up your equation first, right, before you then check your, we're going to check our limit. So I'm going to plug in. So 1 over 2 times infinity squared, right, becomes 1 over infinity, which is equal to 0. Okay, 1 over a super, super big number is a super small number. Okay, the biggest problems that I saw were people didn't show this and they didn't write this. Okay, maybe you plowed through and did all the derivatives, but if you're not telling me what you're doing, you're not going to get credit for it. Okay, so question number 1. Like I said, the solutions for this are up online already, but I just wanted to reiterate, what you guys need to do, because, the quizzes, all together, our quizzes are worth, I think, like 40% of our grade, but we dropped the 2 lowest quiz scores. Okay, so individually, the quizzes aren't worth as much as the final exam, which is 30% of your grade. Okay, so all of these points on the final exam, you don't want to be losing a couple points here, a couple points there on your final exam, right? You want to be building up all that credit. Okay. All right, so let's talk about question number 2. This was another one that I saw. Limit as x goes to 0, sine of 2x plus 7x squared minus 2x all over x to the 4th plus 2x cubed plus x squared. Most of you guys have the right idea. Okay, you guys have a pretty clear understanding about what's going on, and you have a pretty good idea about what to do, but there were some details where you lost points. Okay, so our check is, right, I'm going to plug in 0. So I'm going to get the sine of 0, plus 0 squared minus 2 times 0 all over 0 to the 4th plus 0 cubed plus 0 squared. Sine of 0, right, that's equal to 0. So this is 0 over 0, which is an indeterminate form. Okay, so I must show this before I proceed. Okay, if I don't show it's indeterminate, then what's your justification for doing L'Hopital's? All right, L'Hopital's rule, let's go ahead and do it. So L'Hopital says we've got the same limit bounds as before. I'm going to take the derivative of the top. So derivative of the sine is cosine of 2x plus our chain rule. So this is 2 cosine of 2x, right? 7x squared becomes 14x minus 2. This derivative of the bottom is just a polynomial, 4x cubed plus 6x squared plus 2 times x. Okay. Again, we have to do a check to see what it is. So this is going to become 2 times the cosine of 0 plus 0 minus 2 all over 0 plus 0 plus 0. All right, let's take a look. Cosine of 0 is equal to 1 2 minus 2, that's equal to 0 all over 0. So we're still in indeterminate form. Okay, I need to do L'Hopital's again in order to okay, remember, I checked it. I stated my next process. Okay, for each step, you have to do that. Okay, let's go ahead. So limit as x goes to 0. So I take the derivative here. So I've got my 2 from before. I've got my 2 from my chain rule that I know I'm going to carry. And I've got my minus the sine of 2x. I'm taking the derivative of the cosine of 2x. Okay, plus 14 minus 0. This is going to be 12x squared plus 12x plus 2. Okay, I just took the derivative of the bottom. And now let's do a check. So this is going to be minus 4 times the sine of 0 plus 14 all over 0 plus 0 plus 2. Sine of 0, we said that before, that's equal to 0. So we have 14 over 2, that's equal to 7. So that's what our limit is finally equal to. Okay, but see what I did? I checked, I showed it was indeterminate, I stated what my next process was. I did it. I checked, showed that was still indeterminate, stated what my next step was going to be, and I checked it, and I have an answer now. If this was still indeterminate, I would take L'Hopital's again and see what happened. Okay. Questions for you guys all seem to have, so I'm not going to worry about that. Question 4, obviously you have too. Don't worry about that either. Okay. But like I said, I posted this to our website right underneath where the quiz is. So let's see. So this week, coming up, we have a quiz on Thursday. Our quiz will be chapter 4.1 and 4.2, both parts. Part A, part 1, part 2. We're going to finish up part 1 today, and then we're going to do part 2. Okay, you guys have homework for 4.2, which was posted last week, and then homework for 4.2, which is chapter 1.1. Part 2 is posted this week. Okay, so you guys should be able to see that as well. We'll talk about those part 2 on Wednesday. All right, before I get going on finishing up part 1, does anybody have any questions on homework problems? And I realized I said I was going to post a question 4.1 and I forgot, so I will do that later. Today I'll scan that in and post that. Uh, 25 and 26. All right, let's take a look. Okay. Okay, so this is homework chapter 4.1. This is question 25. Okay, so 25 says y prime 2 of x equals minus 2k e to the minus 2x, y2 double prime x equals 4k e to the minus 2x. Let me just make sure I didn't have anything. Oh, I'm sorry. I looked at the wrong page. This is like part of the answer. So let me start at the beginning. So this one is y1 and y2 are solutions to a differential equation. So y double prime plus 7y prime plus 10y equals 0. Y1 equals c e to the minus 5x. And then y2 equals k e to the minus 2x. Okay, so now I think we're supposed to figure out what the c's and the k's are. All right, so let's go ahead. So this one, so we're going to start, you can just ignore that. We're going to come up to that in a minute. So we're going to substitute into our equation, right, this equation here. So what I'm going to get is 25c e to the minus 5x. Right, so that's this right here. So I had to take the derivative twice, okay, because that's the second derivative. 7, right, I'm going to do this here. The first derivative minus 5c e to the minus 5x plus 10, right, c e to the minus 5, that's a 5x equals 0. Now I'm just going to start working my way through. So this is going to become 25c e to the minus 5x minus 35c e to the minus 5x plus 10c, sorry, CE to the minus 5x equals 0. Okay, let's see, so if I've got y2 prime of x equals minus 2k e to the minus 2x, y2 double prime 4k e to the minus 2x. We're going to substitute these. Right, so first we did it with y1, and now we're going to do it with y2. We're going to substitute it into the equation. So this is what we have first. Okay, so I'm going to substitute those into the equation. So now what I'm going to get is 4k e to the minus 2x plus 7 times minus 2k e to the minus 2x plus 10. Goes now put a question mark. Is that really true that those are equal? So 4k e to the minus 2x minus 14k e to the minus 2x plus 10k e to the minus 2x equals 0. Okay. Right, so they're both solutions, right? Because if I add these, I'm going to get 14 minus 14 gives me 0, right? And then this one is going to be 35, or 25 plus 10 is 35, minus 35 is equal to 0. So they satisfy. So we were given an initial differential equation, right? And we were given y1 and y2, and we're asked to figure out our y1 and y2 solutions to this equation. And so what we did was we found the first derivative and the second derivative for y1. We plugged those values into the equation, and the equality came up to be true, right? 25 minus 35 plus 10 is going to be 0. I did the same thing for y2, substituted it in, like find the derivatives, right? Substituted them in, added them up, and the equality was true, right? That was equal to 0. So they're both, y1 and y2 are both solutions to this differential equation that we were given at the very beginning. Okay, that was 25. 26 is the same thing. So 26, they're both substitutions, both solutions to the equation as well. Let me take a look at 43, because 26 is just like 25. Okay, so 43. You guys have this one here. I'm going to scroll down. All right, so 26 is just like 25. Okay, so would you say 43? So 4.1. Okay, so momentum of an object of mass 10 kilograms moving along an x-axis is proportional to the net force on it. K equals 0.5 kilogram meters per second per Newton. Okay, so this is P is proportional to the force, and then T is in seconds. So we want to set up a differential equation for the velocity, solve the differential equation for the velocity at time t equals 0, which is equal to 1 meters per second, is our initial condition, and then determine the momentum of an object at 10 seconds. All right, so let's go ahead and work it through. So part A says momentum P equals mv, right? And then F equals ma, and then A, remember, is dv dt, change in velocity over time, right? So P, it's proportional to, it's equal to K times F, right? So we have a proportionality constant K. So mv equals Km dv dt. So I substituted my acceleration with dv dt, right? Because acceleration is the derivative of velocity with respect to time. So I've got the function v and its derivative all in the same equation. Okay, so here's how we're dealing with it. So I'm going to rewrite this. This is going to become v equals 0.5 m dv dt. Right, k we were given, so I just plugged in k. So that's part A. But you had to be able to set these two equal to each other. Part B says we're going to solve it for velocity time. So time t equals 0, velocity equals 1 meters per second. So this is our initial condition. Okay, so now I'm going to take this equation here. I'm going to write v of t equals c e to the 0.5 t. Okay, because it's the function equals its derivative, you know, times some kind of constant. When you have a function equaling its derivative, it's got to be an exponential function, right? And then this part here is your constant term. Okay, so now v of 0 equals 1, right? That was our initial condition. So now I can say 1 equals c e to the 0.5 times t equals 0, which is equal to 1 equals c, right? Because e to the 0 is equal to 1, so c equals 1. So therefore, our velocity is e to the 0.5 t. Okay, so we used our initial condition to help us with that. Part C says determine the momentum of an object at t equals 10 seconds, right? You can see how we're just going to plug that in. So this becomes p equals mv equals 10 e to the 0.5 t. So p of 10 equals 10 e to the 0.5 t. That's 10, which is equal to approximately 1484.132 kilogram meters per second. MB, this 10 is not the same thing as that 10. That's 10 seconds. This is 10. This is our mass. And then V, we substituted in V. So this is our mass times V. Okay. That's 43. Okay. All right, so what I'd like to do is I'm going to go back to chapter 4.2/1.1, and we're going to keep working through examples. This is integration by substitution. Okay, we're going to keep talking about that. We've got several examples to work through. And then we're going to start on the second part, which is integration by parts. It's all still a part of the same chapter. Okay, so here I am on my lecture examples. This is where we left off last time. Lecture examples here. We left off at example number 5. So we're going to be taking a look here. So I want to integrate t over 1 plus t squared. So we're learning a bunch of tools in our toolkit for how do we integrate things, integrate functions. So my first question whenever I see an integration is, can I just integrate like normally, like using the power rule? Okay, so if I do the power rule, well, I can't do the power rule. I get like a sort of complex function. I can't just, you know, add 1 to the exponent. It doesn't make sense, right? I can't do trig, I can't do whatever. But my next question is, right, do I have a derivative of a function? Like if I've got a complex function, 1 plus t squared, t is the derivative for t squared. So if this is the derivative of this function here, then substitution will work really well, okay? So I'm thinking I usually substitute the more complex part of it, okay? So u equals 1 plus t squared. Remember, you have to take that derivative. Du equals 2 times t dt. Well, look, I've got t times dt, but what I just solved for is 2 times t dt. So I'm going to divide both sides by 2. So I'm going to get du over 2 equals t dt. So this, I'm going to substitute t dt with du over 2. Okay, so let's go ahead and substitute. Right, so I'm going to get 1 over u times t dt. I'm going to substitute in du over 2. This du times 1/2, right? I'm going to take that 1/2 out of my integral. So this is 1 over u times du. Remember, this is u to the minus 1, right? I can't just do the power rule on that. I've got to do my natural log. So this becomes 1/2 natural log, absolute value of u plus c. I'm not done. I have to substitute back for u. Okay, so this becomes 1/2 natural log of 1 plus t squared plus c. Don't forget the absolute value. When we are taking the natural log of a function, because we've integrated, we have to restrict the domain. The domain has to be positive. That's why we take the absolute value. It's going to be positive here because we're squaring the t squared, but it's always a good habit to get into where you're taking the absolute value of it. Be careful, don't stop, right? Your answer is not in terms of u. You have to substitute back because your answer, you started with t. So we need to come back to where we were. We have to substitute back in for our original equation. All right, let's go ahead and do this one. Example number 6. All right, so can I do power rule? No, there's no trig, nothing's gonna work. All right, let's take a look. So I've got my more complex function is 4x squared plus 1. And I know I'm doing a quantity squared on. I'm not gonna worry about the quantity squared just yet. 4x squared. So if I take the derivative of my complex function, I'm gonna get some constant times x. Well, let's look at what we have. I have some constant times x. So my derivative is of this function is right here. Okay, so that's a good candidate for u substitution. So u is equal to 4x squared plus 1. I take that derivative, I'm going to get 8x dx. Now you may be asking, why don't I substitute for the whole thing? 4x squared plus 1, quantity squared. Think about it. If I go to take that derivative, I have to do 2 times that equation, 2 times 4x squared plus 1, and then do my chain rule, then times 8x. So now I have 2 functions being multiplied together. It's much more complex, right, than if I just substitute my inner function, because I can integrate 1 over u squared, okay? So I've got 8x dx. Well, I have 8x dx right here, so that's what I'm going to substitute for. I don't have to rewrite this stuff or divide by anything, okay? So let's go ahead and substitute. So this becomes 1 over u squared times du, okay, which I'll write as u to the minus 2 du. Okay, now I'm going to do the power rule, which means I take this exponent and I add 1 to it, and I divide by that new exponent. And don't forget your plus c. Okay, but we're not done. We've got to substitute back. Right, I have to substitute back in for u. So this is going to become 4x squared plus 1 to the minus 1 all over minus 1 plus c, which I can clean up a little bit, make it look like minus 1 all over 4x squared plus 1 plus c. These two are equivalent. Okay, this one just looks a little nicer. I guess I'll have that. Okay. Example 7, let's go ahead and take a look. All right, so let's ask ourselves these questions here. So I've got a function here and I've got a function here. So I can't just do the power rule because I've got 2 functions being multiplied together. And don't be tempted to FOIL this out and then distribute terms and then do the linearity thing. Okay, the whole point is to be able to recognize that you can do use substitution on here. Okay, so now I've got a function within this x squared. So that's a pretty good candidate, but let's also take a look. So I've got an x cubed and an x squared. Well, x squared is a derivative of x cubed, right? So that means this is a good candidate for my u substitution. So I'm going to say u equals 3x cubed plus 3. My du is equal to 9x squared dx. All right, well, look, I've got an 18x squared dx. So what I'm going to do is this. I'm going to just solve for x squared dx. So I've got du all over 9 equals x squared dx. And what I'm going to do is just to, so I don't have to worry about like, am I doing the right thing? I'm going to take the 18 out of my integral. I'm going to rewrite this 3x cubed plus 3 squared times x squared dx. I'm just going to keep it simple. It'll come out in the right way anyway. This is what I'm substituting for. This is what I'm substituting for. Okay, so let's go ahead and substitute. All right, so I've got 18 times, right? This is u squared times, right? For x squared dx, I'm going to substitute in du over 9. That 1/9 is a constant term. I'm going to bring it outside my integral. So I'm going to show you the steps. 18 divided by 9, u squared du. Okay, let's clean that up. So 18, that's 2 u squared du. So let's go ahead and do the power rule. So don't forget the 2 that you have there already. So the power rule says take my u, add 1, and then divide by that new exponent plus c. And now I've got this in terms of u. I have to substitute back. Okay, substitute back in for u. So I'm going to get 2/3 3x cubed plus 3 quantity cubed plus c. Okay. Questions so far on how we did that? All right, our last example. Let's go ahead and take a look. Scroll that up just a little bit in case you're still writing. All right, I've got a function times a function with a function inside of it. All right, so good candidates for use substitution are the nested functions, but let's just do a quick check. I can't do the power rule, it's not gonna work. The trig functions aren't gonna work because I've got 2 functions being multiplied together. Let's take a look at our derivatives. So x squared, that derivative is equal to x. Well, I have an x right there. Good, so regardless of the numbers, because I can fiddle with the numbers later, I have an x and an x squared. So that means this is a derivative of that. So this lends itself well to u substitution. So I'm going to say u equals 5x squared minus 3. Du equals 10x dx. Let's solve for x dx, so multiply by 10, divide by 10, sorry. So du all over 10 equals x dx. And what I'm going to do is I'm going to rewrite this. So I'm going to take the 20 outside of my integral. And I'm going to go sine of 5x squared minus 3. And I've got x dx. All I did was like kind of move things around a little bit. So I can substitute here. I can substitute here. Okay, so let's go ahead and do that. Substitute. Okay, so I'm going to get 20 times the integral of sine of u times du over 10. Forget that x dx is equal to du over 10. This 1/10 I can bring outside my integral, so this is 20 over 10 sine of u du. You can just make it equal to 2. I wanted to show you where that was going, where those numbers were going. So let's clean that up. So this is going to be 2 sine of u du. Okay, when I go to take the integral of sine, right, I'm going to get the minus the cosine. So this becomes 2 times minus cosine of u du, minus cosine of u plus c. Okay, sorry, I already did that. Now we get to substitute back. Yes, I'm going to get minus 2 cosine of 5x squared minus 3 plus c. Okay, substitution. It's a really nice tool. It's a good first check. Okay, power rule doesn't work. I've got 2 functions being multiplied together. Is one of them a derivative of the other? Good. I'm going to do substitution. These are the questions you need to ask yourself. Okay, because this is 4.2 part 1. We're going to do 4.2 part 2 right now, which is integration by parts, which is another technique we need to employ when we have 2 functions being multiplied together. Okay. Any questions on this before I change gears? Okay, I'll scan this in later and then we'll have it up online on our modules page. All right. Okay, so this is 4.2, chapter 1.1, part 2. Okay, this is our integration by parts. It's a very powerful tool also. Okay, so let's talk about like what do we need to do this? So when we have an integral of the product of two functions, right? I've got, function 1 times function 2, and neither of these two functions is a derivative of the other. Okay, so I've got a checklist. I've got, two functions being multiplied together. Okay, can I do the power rule? No. Can I do U substitution? I have to ask myself that first, okay? If I can do U substitution, I need to take a look. Is there a derivative of one of those functions in here? If there is no derivative in there, then I need another tool to help me integrate these things, okay? So integration by parts is the tool that I'm going to use when I have two functions being multiplied together and I need to integrate them, and U substitution isn't going to work. Okay, so our integration by parts, that whole algorithm comes from our product rule in differentiation. Remember, integration is finding the antiderivative. Okay, there's a whole bunch of reasons for why we'd want to find the antiderivative on something, why we would want to integrate some functions, okay? And we spent the whole semester talking about why we would want to take the derivative, right? So when we do these things, right, integration and derivatives form two sides of the same coin, okay? So it stands to reason that I'm going to be able to derive one method from the other. So let's remember our product rule, right? I've got two functions being multiplied together. So I've got U of t and v of t, right? And I want to take their derivative with respect to t, right? This is our product rule. And we said we're going to do the first times the derivative of the second plus the second times the derivative of the first, right? So that was u prime v plus u v prime. And we're adding, so it doesn't matter which order we do it in. So what I'm going to do is, instead of writing u prime and v prime, I'm going to write du and dv. So this is going to become v du. I'm going to rewrite it. So this is du, and that's v, plus u dv. Okay. So now, and I've got this derivative of these two functions here. Okay. What I want is, if I go to integrate both sides, let's say integrate both sides, because I'm looking for the integral of these. I want to find the integral of my two functions being multiplied together. So I've got the integral of the derivative, right? I'm going to drop the t, u times v equals the integral, right, of v du plus the integral of u dv. Okay. So this is the thing here that I'm going to be solving for. Because when I integrate a derivative, what do I get? I could just get u times v. U times v equals v du plus u dv. Okay, if I'm solving for this, I'm going to say this equals that. So this, I'm just going to write it this way. It's the integral of u dv equals uv minus the integral of v times du. In case you're not sure about my handwriting with the v's and the u's, the u has a little hook and the v does not. Okay, this right here is our integration by parts formula. Okay, we're going to be given this. We're starting off in a form that's the integral of u times dv. It's going to be our choice what to assign as u and what to assign as dv. Okay, but this is where we start from, and then we have to come up with all the rest of these pieces in order to work it through. So let's write down some stuff about integration by parts. Okay, so why do we do this? We've got the product of two functions, right? So two functions are being multiplied together. And integration by substitution isn't going to work. Right? One of them is not the derivative of the other one. Integration by substitution isn't going to work. So what do I need to do, right? One of the functions is in derivative form. That's our dv. It's not the derivative of the other one. It's just a derivative. This is dv, okay? And the other one is a function that we're going to take the derivative of. So we must choose u and dv wisely, right? It's not the end of the world if you choose them wrong. You'll just notice that you did it wrong and it isn't coming out right. So let's think about it. So if I choose, we choose u. One of the functions equals u. One function. We choose to be u. What I do with that is I take the derivative. To get du. So I choose this function equals u. I take that derivative to solve for du. Because I have four parts. I have u, v, v, and du I need to find, right? The other function we choose to be dv, right? And I have to integrate to get v. So I choose u, I choose dv. I take the derivative to get du, I take the integral to get v. Okay, we're going to go through a bunch of examples so you can see how this stuff holds together. All right. There it is. So I've got the lecture examples for chapter 1.1 part 2. Here we're going to roll through a bunch of examples so you can see how all this stuff holds together. And we're going to choose correctly, we're going to choose incorrectly. So you'll see like, uh-oh, I made a mistake. I need to choose something different. Okay, it's not the end of the world if you choose it incorrectly. And we'll talk about like how we can fix it. Okay. All right, so the first problem, I've got z times e to the z dz. Okay, what I like to do is I'm just going to write down my formula at the top. U dv equals uv minus integral of v du. Okay, every time I do one of these problems, I write down the formula, and that helps me remember what do I need to do. Okay, if you guys have had calc before and you've learned this method, some people have talked about there's some kind of mnemonic to help you remember. I don't care, you want to use that, that's fine. I like to kind of think it through. All right, so I'm looking through this. So first off, when I first look at this integral, I go, can I do the power rule? I've got z e to the z. I've got two functions being multiplied together. Okay, so I can't do the power rule. Two functions being multiplied together means either use substitution or integration by parts. So let's try use substitution first. So use substitution, z isn't a derivative of e to the z. E to the z isn't a derivative of z, so neither of them is a derivative of the other one. So use substitution won't work. So I need to choose, I'm going to do integration by parts, and I need to choose u and dv in order to figure it out. So I'll tell you ahead of time, we're going to make the good choice, and we're going to do the bad choice. So you can see how, oh, the bad choice isn't working out. So first we'll do the good choice first. Good choice meaning I chose u and dv correctly the first time. And it's trial and error. You guys are going to be doing these homework problems. You're going to try it out. Sometimes it'll work, sometimes it won't. And you're going to be able to recognize when you have to backtrack and switch your variables. Okay, so my first time through, I'm going to go u equals z, right? So I've got a u and dv. This is the form that I'm looking at. So I have to assign one of these functions to be u. I have to assign the other function to be dv. So if I have u, then I need to take the derivative. So the derivative of that is just simply dz. See how when I did this, I made it more simple, right? I got rid of a power, right? So that was good. I made it more simple. Now dv is what's left over. So e to the z dz. To get v, I have to integrate both sides. The integral of e to the z is e to the z. Okay. So now we're going to put this together in our uv minus v du form. So u v minus v du. Okay, this just becomes z e to the z minus the integral of e to the z, we already said was e to the z. Now don't forget your plus c because it's an indefinite integral. Next semester in Calc 2, we'll do integration by parts, but with bounds on them. So you can see how it's slightly different. So it's a good choice, right? I simplified it, it worked out really well. So let's do the bad choice. So you can see bad choice. So you can see how if we don't assign u and dv correctly, what happens. So let's do it the other way. So u equals e to the z. My du equals e to the z dz. All right, that didn't really get me much, but let's keep working. So dv equals what's left over, z dz. So to get v, I have to integrate. So that means I'm going to do the power rule here on my z. So that's going to be 1/2 z squared. Don't worry about the plus c's. We're going to add them at the very end. Okay, let's plug it in. uv minus v du. So u, e to the z, v, 1/2 z squared, minus v du, 1/2 z squared, and then du is e to the z dz. Oh, look, it's more complicated than I started with. Gated than my original. An original problem. So that's a hint, right? When I see this, maybe I need to stop and then switch variables, u and dv, and then try again, right? It's going to happen, right? You're going to choose incorrectly. It's going to get more complicated. I have to do this again. It's going to be crazy. So now maybe just stop and just try it the other way. See if I switch my u's and my dv's, it will be easier to work it through. Okay, trial and error. There's a little bit of trial and error on all this. Okay. We'll try example number 2. So example number 2, let's go ahead and take a look. Z squared e to the z dz. We want to integrate. All right, so I've got two functions being multiplied together. My first question is, can I do u substitution? Well, I don't see a derivative of the other function, so no u substitution. So I need to think about integration by parts. So I'm going to go uv minus integral of v du. Okay, so this is what I'm doing, my process. It helps me remember. If I write the formula down each time that I'm working it through, I'll memorize it. I'll remember what I need to do. So we figured out last time it's easier if I assign u to my z squared, my z. So my du in this case is 2 times z dz. Okay, my dv is equal to e to the z dz. I need to integrate. Oops, I'm going off the page here. That's going to give me v equals e to the z. Okay, so let's put it together in our uv minus v du format. So u, z squared, v, e to the z, minus the integral of v du, e to the z, times 2z dz. All right, let's, I'm going to take the 2, I'm going to bring it out. So I'm going to get z squared e to the z minus 2 times the integral of z e to the z dz. We just did this, right? So I need to do integration by parts again. Okay, It's okay if I need to do it multiple times. So I'm going to remember, right, how I assigned my u and my dv. So my u will be z, my du is dz, my dv is e to the z dz. I take the integral of both sides to solve for v, I get e to the z. Okay. The trick here is to carry through what you've already accumulated. So what I've already accumulated is z squared e to the z minus 2 times uv minus v du. So minus 2 times, I'm going to plug that in. So u, v, minus v du, and bracket. This is really important that you have the brackets because we're subtracting. I need to make sure I distribute all those negatives to the correct spot. So now I'm going to get z squared e to the z minus 2 times z e to the z, right, minus e to the z, and then there's a plus c in there. Okay. So let's go ahead and distribute our -2 to all of these terms. So I've got z squared e to the z minus 2z e to the z, negative times a negative plus 2e to the z. And I'm just going to say I could multiply by -2, but 2 times c is still a constant term. And then I'm done. You don't have to factor out an e to the z or anything. You could just leave it like that. Okay, we did it twice. Okay. You guys good? Okay, so example 3. This is a trick question. Right, I want to take the integral of the natural log. A common mistake that I see a lot is people, they take the derivative of the natural log. This is your derivative. Okay, if I take the derivative of that, I say, oh, that's equal to 1 over t. Well, that's taking the derivative of the natural log. So be very careful. We're taking the integral of the natural log function. Okay, so which means I can't do the power rule. I can't just plow right through it. And substitution isn't going to work because I don't have a 1 over t somewhere, right? If this was ln of t over t, I would do u substitution because my derivative would be in this function, but I don't. So ln of t times dt, you don't realize, but we actually have 2 functions being multiplied together. ln of t times 1. Okay, so we're going to use those as our u and our v. All right, so now how do we assign our u's and our v's? So let's think about it. Remember, I'm going to take the derivative of whatever I assign. Let's do it wrong first. If I assign u to be dt, I take the derivative, I'm going to get the second derivative. That doesn't make sense, right? Also, if I assign dv equals ln of t, then I go to integrate it, and then I'm back where I started from, right? So if I have u equals the natural log of t, du equals, I'm going to take that derivative, 1 over t dt. Okay, I've already made it more simple, right? I've gotten rid of my natural log function, and now it's just 1 over t. So that means dv is what's left over dt. Take the integral, v equals simply t. Just remember our format, uv minus the integral of v du. Okay, that's how we want to do this. So let's put it together, u, ln of t, times v, t, minus the integral of v, t, times du, 1 over t, dt. So let's clean this up. So this is t, ln of t, minus t times 1 over t, that's just equal to 1, dt. T, ln of t, minus t, and don't forget your plus c. Right, remember, if I take the derivative of this, I'm going to be back to ln of t. I need the product rule. This would go down to 1. It would simplify, 1s would cancel, and I'd just be left with ln of t. Okay. All right, let's apply it here. So remember, we're going to go uv minus integral of v du. So I have to assign my u's and my dv's right. Okay, let's do it wrong first so you can see when we need to backtrack. So I'm going to say my u equals t to the 5th. My du equals 5t to the fourth. That's usually a good place to start, right? Maybe that works. Let's see if my dv equals ln of t dt, and I have to integrate. Well, we just did that, right? So my v is going to equal, I have to do integration by parts here in order to solve for v. So more complicated than need be. So I'm going to switch. So stop, switch variables. Try it again. Okay, let's try it. So I'm going to switch. So my u, I'll try as ln of t. My derivative is 1 over t. Already it's getting more simple. My dv is t to the fifth dt. I go to integrate. Well, integrating with a polynomial, I increase my exponential by 1 and I divide by that. Okay, that's not so bad. All right, so let's plug that in and our uv minus integral of v du. So u, ln of t, v, 1/6 t to the 6 minus integral of v, 1/6 t to the 6 times du. Well, there should be a dt in there. 1 over t dt. Okay. Let's clean it up a little bit. I'm going to bring out the 1/6 t to the 6th ln of t. I'm going to take this 1/6 outside. Now watch, I have t to the 6th divided by t. That reduces my exponent by 1, so t to the 5th dt. Don't be fooled in thinking, you know, you've got the 1/6 there already. I don't have to do anything more. You still do. You're carrying this through. The 1/6 gets multiplied by whatever you find in here. So this is going to become 1/6 t to the 6th ln of t minus 1/6 times. This becomes t to the 6 all over 6. And then don't forget your plus c. Okay, I'm going to multiply these together. 1/6 t to the 6 ln of t minus 1/36 t to the 6 plus c. Okay, be careful. It's a common mistake. People think, I've got the 1/6 there already. I don't need to do it again. This 1/6 is a multiplier that you inherited from before. Okay, it's a multiplier. So make sure you carry that multiplication through. Our last example is kind of a trick solution. Not really a trick, but it's a different way of thinking, kind of thinking outside the box. It's kind of like you guys have a homework problem like this, and sometimes this kind of a question pops up on the final exam too. So let's go ahead and work our way through it. So example number 5, e to the x cosine of x dx. All right, so let's ask ourselves these questions. Can I do the power rule? No, I can't just do a trig because I've got the e to the x there. Well, can I do u substitution? Well, neither of these is a derivative of the other, so substitution isn't going to work. So integration by parts is going to work. Oops. Okay, so this is the form I need to think about. Now here, let's just take a quick look, right? E to the x, I can take the derivative as e to the x, take the next derivative and the next and the next. E to the x and cosine both are part of a special class of functions, so they have an infinite number of derivatives, right? I can go on forever taking derivatives of e to the x and never reach the end. Unlike a polynomial, right, where ultimately I'm going to get down to 0. Same thing with cosine, right? I may loop around. I'm going to go cosine, I'm going to get the derivative. It's going to be minus the sine, then I'll take the derivative of that, minus the cosine, take the derivative again, there'll be sine, and then we'll be back to cosine. So it takes about 4 repetitions, but we never get to 0. It just loops. Okay, so this has also an infinite number of derivatives. Same thing with integrals, right? They're infinite. So what I assign as u and what I assign as dv is arbitrary in this case, okay? Because neither one is going to make it more simple. That's why there's a trick solution. And the trick solution is we're going to be thinking of this as both sides. We're going to work both sides of the equal sign, okay? You'll see as we work it. So when I choose u, I chose u to be e to the x, but you could have just as easily have chosen it to be cosine. If you choose u to be e to the x, when we do integration by parts again, which we will in just a minute on this problem, choose u to be e to the x again. Okay, so keep it consistent. So du equals e to the x dx. So dv equals cosine of x dx. We take the integral, I get sine of x. Okay, so I'm going to plug that into my uv minus v du. So u v minus v du. Oops, sorry, e to the x dx. Okay, so here I need to do integration by parts again. Right, I have two functions being multiplied together. I can't do u substitution. I've got to do it again. So let's do it. So u, remember I said we're going to choose the same format that we did before. U equals e to the x, du equals e to the x dx, dv equals sine of x dx. I take the integral of both sides. I get v equals minus the cosine of x. Okay, I'm taking the integral here, not the derivative. All right, so let's plug that in. So let's remember e to the x sine of x. We have to keep track of what we've had before. Okay, minus, I'm going to put a bracket around it because I'm subtracting. I'm going to do the uv minus v du integral. So I need to subtract. I have to keep track of my multiplying by negative. So I put a bracket. So u e to the x, v minus cosine of x. Minus the integral minus the cosine of x e to the x dx. Okay, well, this is going to become plus cosine of x e to the x dx. Well, look at where we're at. This is our original problem. Well, if I keep thinking I'm going to do integration by parts, I'm just going to, I'm not going to be solving anything. I'm just going to be making this a bigger and bigger problem, right? So this is where I need to think outside the box. So this was equal to this. I'm going to work both sides of the equal sign. It's not an identity, it's a function. So I can do that, right? So let's write it again. So I've got e to the x cosine of x dx equals. Let's write it all out, and we're going to keep track of our negatives. Okay, so I'm going to get e to the x sine of x minus a minus plus e to the x cosine. Oops, I can't see what I'm doing. Minus plus cosine e to the x. Okay, this is going to be minus times plus. That's going to be minus the integral of e to the x cosine of x dx. Okay. This is where we started. That was our original problem. This is where we've got so far, okay? And I can't just keep trying to work it with integration by parts. I'm not going to get a solid solution, so I have to work both sides of the equal sign. So I'm going to deal with this integral as a commodity. I'm going to add it to both sides of the equation. So I've got this one plus this one. I've got two of them now. E to the x sine of x plus e to the x cosine of x. And then let's add in our c while we're here thinking about it so we don't forget. Well, I wanted the solution for just e to the x integral of e to the x cosine of x, not 2 times the integral. So I'm going to divide both sides by 2. So I'm going to get the integral of e to the x cosine of x dx equals e to the x sine of x plus e to the x cosine of x divided by 2 plus c. I could have done the plus c divided by 2, but that's still a constant term. And this is your answer. We're accustomed to thinking about, I'm going to get a solid solution and that's what it's equal to. But in these types of functions where both of those functions have an infinite number of derivatives and an infinite number of integrals, I have to be more creative about how I'm solving this. I have to work both sides of that equal sign. Okay? That's it. I think you've got a homework problem that's something like that. And that's the end of chapter 1.1. We have 2 more tools in our toolkit: integration by substitution and integration by parts, plus the power rule and our trig functions and the other stuff that we talked about before. Okay. 4.1, 4.2 will be on the quiz on Thursday. Okay, we can go over these homework problems for this part chapter. It's part 2. We'll go over those homework problems on Wednesday. Okay. All right, you guys. Have a great day.
Thank you. Have a good day.
Thank you.
Thank you.
Bye.
Thank you.
Bye. Take it easy, guys.